We will be able to sort this out if we can answer this question, which is if y is exponentially distributed with parameter a lambda, then which random variable is distributed exponentially with lambda? So if we can answer that question, we can make all the previous those delta tj's IID also by maybe doing some little bit of scaling. So let's start with the basics. So if y is exponential with parameter a lambda, then the CDF is 1 minus exponential of minus a lambda times y. So then if we were to divide y by a, then the right hand side becomes 1 minus exponential minus lambda y. So then we could interpret that as ay is less than little y, less than or equal to little y. So clearly then, what is exponential with parameter lambda? It is ay. A times capital Y is the random variable that we are looking for. So with that in mind, that if y is exponential a lambda, then ay is exponential lambda, we can fix that non-identical problem that we just mentioned. So all the tj's, as I said, are exponential with parameter n minus j plus 1 lambda. They're mutually independent, and we already know if y is exponential a lambda, then ay is exponential lambda. Hence, n minus j plus 1 delta tj has to be exponential with parameter lambda. So now we have scaled all these exponentials to have the same parameter. So that gives us a way forward. So then we can have our samples from an exponential distribution with the same parameter lambda. Lambda is 1 by mean. So what are these R samples? The R samples are n times tau 1, n minus 1 times tau 2 minus tau 1. So all these differences are basically the time between failures. So delta t is the time between successive failures. So that's how we have n tau 1, which is the time to the first failure, n minus 1 times tau 2 minus tau 1, which is the time between the first and second failures, n minus 2 times tau 3 minus tau 2, which is the time between second and third failures, and so on, until n minus r plus 1, tau r minus 1. So each of these terms is a realization of an exponential random variable with the same parameter lambda. So their sum will be r times mean, and here we are going towards an estimation problem, which is a bit too simple. We are not going for method of maximum likelihood or interval estimation, as we have said, but we want to get a good answer quickly. So this simplifies to all the taus 1 through r, the sum of all tau 1 all the up to tau r, and then n minus r times tau r, so the last recorded failure time, that is equal to r times the estimated mean. And if now we plug in the three values, r is equal to 3 in this example, we get a mean, an estimated mean of about 676 hours. So this is quite good. So what we did was we just had 3 failures and 3 recorded instances. We started with 9 samples. We did not wait for all 9 of them to fail, and now, because we knew that the time to failure is exponential for each of them, we were able to go through the mathematics and come up with a good estimate of the mean time to failure. Now, we could wonder that with this problem statement that we started with, what if we, instead of going with this independent exponentials, which by the way would lead to a gamma distributed or an Erlang distributed random variable for the sum, and we could show later on that this estimate is biased because the way it's been computed, but we will not go into those details of more advanced statistical concepts. But let us come back to this, and what if we did not go through all that trouble and we just solve this problem with regression? What do I mean by that? I mean is that we have, basically what we have is our point estimates, our number of point estimates of the reliability, Ri at times Ti. So 3 times have been recorded. We have 3 reliability estimates corresponding to that of an item with exponential TTF. That's important. That is very helpful. So can we not estimate lambda from just this information? Can we not fit a curve? Can we not do regression analysis? So we have R 8 by 9, 7 by 9, and 6 by 9, and the corresponding T's are 144, 182, and 243. So we need to obtain the best fit line between these 3 points. So what is the step? So we'll just go step by step as we do in linear regression analysis. So we have a function relationship which is R equals exponential minus lambda t. We need to linearize, and that's log R is minus lambda t. And then we just minimize the squared error between the theoretical value and the observed value. So that would be minimize sum of the square deviations. There's a plus sign there because of the negative lambda t in the previous line. So we need to minimize this sum with regard to lambda. So now we are in familiar territory. We can get the expression which leads to this minimization, and it turns out that the estimated lambda would be the ratio of the sum of t log r over the sum of t squared. So this would be another way of estimating the mean time to failure, and we can solve this with the numbers that we have, and it's not too bad. The mean is 700, so very much within the estimate that we did from the independent time between failures approach.